In this video, I will discuss how linear kinetic energy is related to rotational kinetic energy. So we use the example of a mass, which I have here, a mass moving with a certain velocity. So what is the kinetic energy of a mass moving with a certain velocity? 1/2 mv squared, right? Does it depend on the direction? If it's moving to the left, to the right, does that matter? If it's moving up or down, doesn't make any difference. It only depends on the speed, not the direction of the velocity. All right. So now what if we apply a force perpendicular? So if we take a mass on a string, as it goes around, the string has a tension force pointing toward the center, but the speed of the ball is constant as it goes around. That tension does not change the speed of the ball. It changes the direction of the motion, but changing the direction doesn't affect the kinetic energy. And one way to see that is to think of work. So does the force do any work on it? Work is force times distance times the cosine of theta, where theta is the angle between the force and the direction it's moving. Well, at any point in time here, if it's moving this way and the force is that way, the distance that it moves is perpendicular to the force, so theta is 90 degrees, and cosine of theta is 0. So that means the string, this tension force in the string, does no work on the ball. I drew the same picture. So we've got Vt, we've got a tension, we've got a mass, and we have a radius. What is the kinetic energy of this mass in terms of m, r, and omega? We just figured it out for m and v. It's 1/2 mv squared. Can we convert it? V, up there, this is Vt, r omega. So 1/2 m r omega squared. What if there were two equal masses, both m over 2, being whirled around at the same distance r? So instead of having a single ball that I'm spinning around, I break the ball in half, and I spin half of it here, half of it there at the same time. Then what would the kinetic energy be? This time we'll have to add up the 1/2 mv squareds. There's an m over 2 here, an m over 2 here. So if we add an m over 2 v squared to an m over 2 v squared, it should be the same. If I took my single ball and split it into two half balls, spun both of them around at the same speed, it would have the same kinetic energy. What if I split it into 4 or 8 or 20 or 9,750 different balls? Add all their masses up, it'll be the same mass, they'll be at the same distance, the same speed. You'd actually have the same kinetic energy. So if there was a complete ring of mass m, at a distance r from the center, we would have the exact same kinetic energy as this from up here. 1/2 m r squared omega squared. And if you look here, you can see kr is 1/2 I omega squared. That means mr squared has to be I for a ring or a hoop. What if we split the mass up differently? We still break it in half, but instead of putting half of it at radius r down here, we bring it in closer to the middle. How would that affect it? Now, if we keep the same omega, kinetic energy is 1/2 times the first mass times the radius of the first mass squared times omega of the first mass squared plus all the same thing for the second mass. But the omegas, if it's on the same piece of string, the omega is constant for both of them. So the omegas are both the same. Masses are each 1/2, but the r's are different. So 1/2 m over 2, that's m1. r1 is just r. The omegas are the same, so omega squared, plus 1/2 m over 2, that's the mass of this one. Radius of this one is actually r over 2 squared, omega squared. And if I simplify that, I actually get 1/2 times 5/8 mr squared omega squared. So last time, when everything was out at the edge, it was 1/2 times mr squared omega squared. This time there's an extra number in here. So that means the moment of inertia, I, in this case, has to be 5/8 mr squared. So you can see that all we did was change the way we distribute the mass, and it changed what the moment of inertia has to be. That's why all these different shapes have different moments of inertia. And you can see that here in these moments of inertia. So for a hoop, we just looked at that. The moment of inertia is mr squared. The number here would just be 1. When you bring things in, so a disk doesn't just have mass around the edge, it's filled in all the way to the center, so it should have a smaller moment of inertia. And you can see here, if we compare a hollow sphere to a solid sphere would have more mass in toward the center of the axis of rotation, and 2/5 is smaller than 2/3. For a rod, this one doesn't have an R, it has a length, so it's like the length of a rod. If I hold it in the center, then the mass is all close into the middle, so this number is small. If I hold it at the end, now the mass is farther away. And since the mass is farther away, the moment of inertia is larger. 1/3 is much larger than 1/12.